So, gentlemen, first little activity. I haven't provided you any room for this in your booklets. My apologies for that. But here we have a 0.108 kilogram wooden ruler, okay? And at the moment, it's not in rotational equilibrium. I have placed a 0.5 kilo mass at the 5 centimetre mark. I've placed the pivots at the 25 centimetre mark. The centre of mass of the ruler is at the 50 centimetre mark. And then at 80 centimetres, I've placed 400 grams. Let me just check. 1, 2, 3, 4, 5, 6, 7, 8, 9. 400 grams. Okay? That is not enough to maintain rotational equilibrium. So what I'm then going to do is allow a reaction force to occur on these scales. Okay? That then applies a force upwards to create a second anti-clockwise torque such that it is now in equilibrium. So what I would like you to do, this is a torque diagram showing all the forces and all the distances about the pivot. Could you please determine what the reaction force is that the scale is pushing on the ruler, and then convert that into grams. Then once you've converted it, you can come up and have a look at the value that might be on the scales.
Wait, so it's the 80 centimetre mark from the left.
Well, so you need to determine how far 80 centimetres is from 25. Good luck.
Sir.
Yes.
That's only 350 grams on the scales.
Okay, yeah, I think 1, 2, 3, 4, 5, 6, 7. Thank you, 8. Don't know where the other mass went. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ah, there it is. Okay, that's a little bit better. So, 500 grams, 400 grams, 108 grams. Please determine the reaction force and determine why I don't have any power. Yo.
That's 5 centimetres on the left.
Yeah, yes. So 5 centimetres from the end. 80 centimetres from that end. Get going, please. It's 108 grams, so that...
How much does it actually
The paperclip, the cradle, well, 50 grams, but the total mass is 400. No, he's not. Get going, guys, come on.
That's their weight, not 108 grams.
That's the weight. If you would like me to place some more information, I will do so. Hang on. Okay, so identify that we've got two clockwise... I'm on auto shapes, hang on. We've got two clockwise moments produced by the mass of the ruler and the 400 grams. And then we've got two anti-clockwise produced by the other mass and the reaction force. Okay? So you can have two torques on either side of your equal sign. Yes, Matthew?
Is that the same as the 5 centimetres?
Correct. So you need to determine all the radii.
So are they all in reference to the end?
It's the... Yes, absolutely.
So is the 50 and the 30 in reference to the end?
Yes, and they're 30 centimetres apart, 25 centimetres apart. Okay, so what have we got? We've got 0.25. Okay. Would somebody be as kind to tell me what the total clockwise moment is? No. Really wish I'd screen captured the other lesson. We're not off to a good start. Could somebody mind telling me what the total clockwise moment is?
4.8 meters.
Thank you. And then that one there is obviously 0.98. So 0.55 FR equals, I'm bad at maths, 3.82.
I think it's
Yeah, I don't think your value's right.
Okay, thanks a lot, KK.
2.42.
Then would somebody mind telling me what you subtract 0.98 from that value, Kalis? Can you tell me what that number is?
1.44.
Thank you. And then what must the reaction force be?
2.62.
And then obviously the scales is taking that force and then dividing it by 9.8. So could you now convert that into kilograms for me, please? Say again?
0.27.
Ooh. Oh.
0.267 if you want it.
Okay, and surprisingly, no one has come up to have a look at the mass on the screen. It's 271 grams. So, not too bad. Obviously, I haven't checked the value. There might be a little bit of friction. There's this mass hanging here that I might not have measured its mass of, but close enough. So, guys, we will find, Evan, if there is not a nice diagram, draw a torque diagram to help you. It'll help you figure out where the pivot point is. It'll help you determine the distances. Okay. So can we now go to our booklets, please, and have a look at this cantilever question. So I've already put in a few things. We have a 300 Newton diving board of length 2 meters. At the very end, we have a 500 Newton person standing at the end. There is a 20 centimetre concrete block. We've got a bit of an overhang of 20 centimetres, and there's a bolt there that's keeping the diving board in equilibrium. Now, with this base, if we lifted the diving board up, it's going to want to pivot at this edge, right? If we wanted it to topple the other way, it's going to pivot at that edge. While it's horizontal, it's in contact with the whole surface. So you could analyse either edge of the block, you could analyse your pivot point. But for this activity, I'd like you to take your moments about pivot point P. Okay? Now, as I said, we've got the distance to the edge of the block, which is producing an upwards reaction force. We've got 1.6 to the edge and then 0.2. So we need to see that the diver is 1.8 metres away. And also 1 metre but 0.8 is not. So I think this distance here is 0.8 metres. Is that correct? Or is it 0.6? No, it's 0.8. We're good there. Okay? So from our pivot point to our forces, that's all I needed to add, and now we've got everything that we need. Please remember, you write everything down. The clockwise moments was going to be 0.8 by 300 plus 1.8 by 500 equals 0.2 F, what did I call it? F reaction force. Okay? I'll do my intermediate calculation. The diver and the board produce a total clockwise torque of 980 Newton meters. So the reaction force acting 0.2 meters away must also produce 980. So FR equals 980 on 0.2, which was 4,900 newtons. Now, we don't know the direction, but we can figure it out. I mean, obviously I've drawn an upwards arrow, but in order for the force here is to the right of the pivot. And so in order for it to produce an anti-clockwise torque, it has to act upwards. Right? If it acted downwards, then this thing's going to be flipping around like a glitch in a computer game. So it's upwards.
I think the clockwise was 1,140.
Okay, that changes things. 1,000.
140.
Okay, 1,140. Could we just confirm that if we divide that by 0.2, we end up with the same answer, or have I made it? 5,000. Ah, thank you. Yep. Oh man, this lesson's going to hell in a handbasket. All right. Now, thank you very much. I had the other force written down. Next thing, gentlemen. Step 2. Solve the vertical translationals. So that's going to be F bolt plus FR plus weight of the board plus weight of the person equals to 0. Okay, so we go 0 equals F bolt plus 5,700 plus minus 300 plus minus 500. Rearrange whichever way you want, and you get negative 4,900 newtons. And so in order to maintain all these equilibriums, the bolt has to be pulling downwards where it's mounted into. So if you had a bolt on that board, obviously that bolt is pulling downwards on the board to maintain rotational equilibrium. Well, that's your homework. So as I said at the start, gentlemen, you could have chosen to analyse the pivot about, not the bolt, so let's call it orange, P. So you can just as well, just like the painter's trolley question, or whatever it was called, the painter's thing, you can analyse the other pivot. Then obviously you would solve for F bolt first, you would get this value, 4,900 first. Then you can analyse the verticals and you would get FR. Okay? Now, guys, that is it for the... Oh, hang on. No, it's not. We've got this question over. We're still looking at verticals. We haven't brought in the third rule yet, where we look at horizontals. There has been no horizontals. Okay? Now, consider... I've taken this picture, I think I borrowed this question from a Jancoli diagram. Guys, stop talking, please. If you hold your hand horizontal, then the weight force of your forearm, which I've just said, let's take it as a 3 kilo forearm. Obviously, your forearm is not uniform, so I've given that its centre of mass is about 15 centimetres from your elbow, which will be the pivot. You then hold a 1 kilo mass in your hand, and that is a distance of 35 centimetres from your elbow. Now, your bicep muscle has a tendon which fuses into your forearm, and it's about 5 centimetres away from your elbow. Okay? So, from our pivot, you might be able to see I've tried to draw in nicely all of the forces acting from our pivot point. Now, we're going to ignore the force acting on the elbow at the moment because we're going to analyse about pivot point P. So step 1, we're going to try and figure out what the force of that bicep tendon must be exerting on the forearm. Yes, absolutely. So for the sake of this question, Declan and KK, stop. For the sake of this question, we'll just say that yes, the tendon is fused vertically to a horizontal bicep forearm. All right, so writing all that stuff down, 0.15 by 29.6 plus 0.35 by 9.8 equals 0.05 F bicep. So F bicep is going to equal all of that divided by 0.05. Now have a look. We're dividing it by a really small number because the perpendicular distance from elbow to tendon is really small. So it's going to have quite a considerable force, 157 newtons upwards. Okay.
Why is the middle of the arm at 0.15? Why wouldn't it be at 0.175?
Because your arm is not uniform density. There's more mass closer to your elbow, less mass further from. It's not uniform density. So that's why I've told you that's where the center of mass is.
Oh, yeah.
All right.
It's not on our page.
Not
It's up there, yeah.
Yeah, right.
I can see.
Okay. Now, have a think. If you held a 10 kilo mass in your hand and held it horizontal, then this is going to go up, nearly by a factor of 10. A 10 kilo dumbbell, your tendon is going to be exerting, 1,500 newtons of force. It's a really large force. Your tendons have to be really strong. It's not very well engineered. So we have evolved to have these long, lanky limbs. If you wanted to minimize your force, it would be better to have the tendon fuse in at your wrist. It would be better if we were like these pterodactyl creatures that had these webs of muscle that went from shoulder to wrist, and then we would be stronger. But because we want to have long, lanky limbs, the tendon has to fuse in quite close. The next thing, if you follow the logic, if I was to hold the dumbbell vertically, this diagram would suggest that from tendon to elbow, there'd be 180 degrees. And that would be dividing it by sine of 180, you would end up getting an infinite force. And that's not quite the case. So you can curl from a vertical point, because when your tendon goes around the elbow joint, it does fuse in at an angle that is not 180 degrees. So there is going to be an angle less than 180 degrees. And so yes, you can curl your hand up. All right. So it is a simplified diagram. Now, here is a Mr. Murray prediction of what could be in a WACE exam. Suppose, because these are all easy questions and I'm expecting you guys to do well with these questions. Suppose that the person placed their arm at an angle of 45 degrees below horizontal, such that now the angle between the weight forces is now 135, and then the biceps tendon would now be 45. Okay? So let me just go and label my forces. F bicep, F arm, F weight. The question is, would there be a difference in the force of the biceps tendon? Would it increase? Would it decrease? Would it stay the same? I'm just going to quickly show you the answer. Some of you might want to quietly ponder the result, but it comes out quite interesting. So let's write it down. We'll go R arm, F arm, sine 135 plus R weight, F weight, sine 135 equals R bicep, F bicep, sine 45. For the sake of this proof or answer, I'm going to factorize out sine 135. And then if we solve for FB, have a look what happens. We get sine 135 over sine 45. Good, cancely. So sine 135 and sine 45 are the same value. They're just on the other side of the unit normal. And so that's showing that it doesn't change the force on the bicep. Okay? So this is an interesting, and in fact, I could have done exactly the same with this. If I had placed let's raise this retort stand up a little bit. If I'd done that, then really it will have no effect. It's still reading 273 because I've moved it around a bit, but it's still reading exactly the same force. That's reduced, that's reduced, that's reduced. It's reduced by the same factor. You could factorize out your sines and they would cancel. When you end up solving for your unknown, you'd have a sine theta on the top and a sine theta on the bottom. Okay? So again, hasn't appeared yet. They put in a really nasty torque and equilibrium question in last year's WACE exam, and that was the differentiator. It was a 6-mark question, most students getting 2 marks or 3 marks. I only saw maybe 2 kids out of 150 that actually got full marks for that question. We will look at it, when we approach the WACE exam. Okay, now we're now going to the second level of difficulty. We're now going to introduce an X component, a horizontal component. Okay, so consider, I'm just going to describe this diagram. We have a wall with a beam, and the beam is horizontal for now. We'll say that the beam is 4 meters long and of uniform density. So its weight acts 2 meters from the pivot. And then at the end, we place a 1,000 Newton weight. Okay, so we've got the weight of the beam, and we've got the weight of a mass that's 4 meters away from the pivot. And then we also place a cable, which I'm going to draw over with a blue line for my forces, at 4 meters, and we'll chuck it at an angle of 40 degrees. Okay? Now, if we analyze the pivot at the wall, then we can determine what T has to be to maintain rotational equilibrium. Now, before we do so, let's just think. If this cable is pulling the beam towards the wall, then there has to be an opposite reaction force at the wall. Because if it wasn't there, the beam would suddenly accelerate through the wall. So we know that there's a reaction force at the wall. We know that it's going outwards. But at the moment, we don't know if it's pushing up and out or down and out. So I'm just going to leave it for now, and we can solve for it. That's what we're going to do now. We're going to solve for tension, which is step 1, and then we can solve for the reaction force, which is step 2 and 3. Now, if we wanted to figure out what T perp is, here it is. We're going to draw a dashed line vertical. There's my T perp, which is equal to T sine 40. And then we've got Tx for now, we'll just call it Tx. That will be T cos 40, okay? Now, we're going to throw everything in, and the only thing different is it's now going to be Rf sine theta. So let's throw it all in. We'll go radius beam, weight beam, plus radius, weight equals radius, weight, T sine 40. Let's throw all the values in. 2 by 200 plus 4 by 1000 equals 4T sine 40. So we'll combine. T equals, the total clockwise moment is 4,400. And so if we then divide by 4 sine 40, we get the tension as 1,710 newtons. Okay? Remember I said at the start, 90% of questions can be solved using the perpendicular force method. And most of you can sort of see, okay, yep, I've got clockwise, and so T perp, that's what we need to produce the anti-clockwise. We could, and don't write this on the diagram because it's going to make it look ugly, but we could find perpendicular distance to the pivot. All we would need to do is extend our force along until we found R perp. All right. Now, if that's R, then R perp is going to be R sine 40. So you could have solved this using perpendicular distance. It would have been R sine 40t. Well, we didn't do that. We did RT sine 40. So there's just an example of what the perpendicular distance looks like. Now, step 2. And what I'm going to write sideways is this is what WACE wants. So WACE wants this. Okay? So we're going to do the Weiss method because in the marking key, you need to show translational vertical and translational horizontal. But on the other side of that line, I'll show you a nice, interesting way to show that it's in equilibrium. But let's go. Sum of all forces in the Y equals 0 equals weight plus weight. Now, let's identify Ty. There he is there. So, I'm not going to identify the reaction force yet because I don't know which direction it is. But we're going to have Ty plus Fry. Okay? Now, we'll go 0 equals negative 200 plus negative 1,000 plus 1710 sine 40 plus Fry. Okay? Fry equals plus 101 newtons. So we've now been given it's upwards. So now I can come back to my diagram. I now know that my reaction force points outwards and upwards. So I can add that final force at the pivot. I'm just going to draw in, let's make it black, Fr. Okay? So we now know that, and we just solved the vertical component. We just solved Fry. So the last thing we're now going to do is bring in the third rule to solve for Frx. Okay? So, step 3. Sum of all forces in x equals 0 equals Frx plus Tx. And I might just, I'll color code just for my diagram. You don't have to if you don't want to, but there's our horizontal and there's our horizontal. All right, so that's the forces on the diagram. So this one's a little bit easier. They're equal and opposite. So you can go 0 equals Frx plus T cos 40. Frx equals negative 1710 cos 40 equals 1310 newtons right. Yeah, maybe let's show our conventions. So I'm going to say that, well, in this case, I had that convention. I had that the tension was positive. So, you know, that was my convention there. Thank you for reminding me, Trent. Now, remember what I said. You will see this skill everywhere in bearings, in projectiles, velocity, momentum, forces, torque. We found the components. We now need to recombine using Pythagoras and arctan. Put your hand down, please, KK, for one moment. So, magnitude, again, I haven't drawn this to scale, but Fr square root 101 squared plus 1310 squared gives a magnitude of 1314 newtons. And then our angle theta equals arctan opposite over adjacent gives an angle of 4.41 degrees.
Rounds down to 1310, which is the same as the
Yep. So in this scenario, the horizontal component is not significant, but in other questions, the angle is going to be a little bit more obtuse. Combining them all now, Fr equals 1.31 kilonewtons. Right, 4.41 degrees up. Or you could say away from wall, but above horizontal. Let's go up. Yeah, in fact, that's probably better. Above horizontal. Just as a quick exercise, as I said, I want you now to look on the left-hand side We've got 4 forces. Yes, Tom, what was it? Go for it. KK, what was your question? Cool. I asked him to, he just said it anyway. Yeah, in this scenario, the vertical component did not affect the horizontal. Well, yeah, as we saw, it wasn't significant to 3 sig fig. There are 4 forces acting on this object. But the convenient thing is, 2 of them are weight and 2 of them are acting straight down. So I could draw a vector diagram. What were our values? 200 and 1,000. So 200 and 1,000. I could then add my tension. No, sorry, try that again. Tension. And then my reaction force. Since it's in equilibrium, those 4 vectors should all sum to 0, and that's what this is showing graphically. But here's the problem. I didn't know whether FR had a positive value or a negative value. Now, obviously, if you use the sine and the cosine rule, it will tell you. Well, how would it tell you? We've got an angle to T. Outside is 40 degrees, or to the horizontal. We've now got our internal angle, which is 50. And so up here, that angle there is 40. So what we need to do is solve for theta. Now, if theta is greater than 40, then it's telling us that the reaction force is above the horizontal. Or if theta is less than 40, then it's going to tell us that FR is below the horizontal. But I don't like just drawing a diagram that's not to scale. And that's what you risk doing if you do the graphical method. You don't know whether you're writing it correctly or not. So I just want to show you as an activity, because you have the sine and the cosine rule in your data sheet, you could be expected to use it. Okay. By the way, we solved for tension as 1710. So we've got both side lengths. Let me just combine that to 1200. So in the last, well, I'll give you 5-6 minutes to solve for magnitude using the cosine rule and theta using the sine rule. Go, go, go. A squared plus B squared minus 2AB cos C. I probably won't, well, if you want to, calculate it, but you know what you're going to get. You're going to get 1310. Or was it 1314?
Yeah.
And then sine theta over 1314. Oh, thank you. 1200 equals sine 50 over 1314. Theta equals arc sine times both sides by 1200. Take the arc sine. And now, here's the problem. You have to do one extra step. So we get that total internal angle. I'm not even going to check. I'm pretty sure it's 44.41. And so the last thing we do, you never want to express a force with respect to another. You're going to express it to the horizontal or the vertical. So we don't say 44.4 degrees above the tension vector. No, you're going to say 44.1 minus 40. Equals 4.41 or 4.4 degrees. Okay, so I just wanted to show you that as an exercise. You can still do it, but in the waste marking key, there will be a mark for writing all of that. There will be a mark for writing all of that. There will be a mark for writing all of that. These questions are commonly in section 2. Because section 1, you're not going to see determine the reaction force 10 marks. Because if the kid doesn't know how to set up the question at the start, again, they've instantly lost. So what, part A, determine the tension. Part B, determine the vertical component. If you could not solve for t in part A, use a value of. They'll give you a value if you couldn't do part A. Okay? Don't risk it. I mean, if a student wrote that, you really want to put a statement here to say the reaction force is the equilibriant of the vector sum of weight plus tension. You kind of have to tell, you can't just write sum of all forces equals 0. You have to be a little bit more explicit. Okay? Now, that's as far as we got with the other class. I'm going to send you guys an email with a YouTube lesson. I want you to do one extra lesson over the weekend. I hope you don't mind because we've got a little bit more time with no sport training and things being cancelled. Some of you might want to... Yep, that was very funny.
Everyone laughs at it.
It was cancely divided by cancely because I only said one cancely.
No, that sucks.
Many of you want to start preparing for your test on Thursday. You've got the weekend. And I want you guys to get to a point where if you want to, you can start doing the more complicated questions in Pearson's chapter 3.2 and 3.3 and past test papers. So, the other class is going to get a 12-minute video of this page. But since we somehow are 10 minutes ahead, we're going to do this example now. You're then also going to get lesson number 4, which goes for about 34 minutes. All right, I've got the email ready and I'm going to click send in period 2. You'll get that email, go home and watch it. And it'll be basically doing the ladder question on page 37 and this boom bridge question on page 38. But let's have a look at this. This question actually turns out to be a little bit easier. And as we do it, oh, actually it has its own little thing to be aware of. Let's throw a few values in. Let's make this beam 200 newtons of weight, and it is of uniform density. Again, it's 4 meters long. I'm picking nice, easy numbers here. So 2 meters to the center of mass. If we take the pivot here, and then at the end, wouldn't you know it, we place another 1,000 Newton object, and then there is a tension acting in this wire, which is horizontal. Okay? The beam is at an angle of 50 degrees to the horizontal. Now, with everything parallel lines and vertical and horizontal, we now know the angle between weight and line of action is 40 degrees. And the angle between tension and line of action is 50 degrees. So in this question, just be careful that we've now got 2 different angles. So don't go writing sine theta equals sine theta, because now it's going to be sine phi instead. Okay? So, I can draw in my reaction force straight away, because have a look. There's only down forces here. So the reaction force has to have an upwards force. There's an inwards force produced by tension, so it has to have an outwards. So I know for this scenario, my reaction force has to be out and up to maintain all those equilibriums. So we can sketch in the reaction force now. Okay?
Do we know the reaction force will be above the line?
Well, we don't. All right, you're absolutely right. We'll find out in the next 8 minutes whether I drew that correctly.
Okay.
All right? So same deal. Now, guys, at this question, Harry, you cannot analyze the pivot up here because we don't know what the reaction force is doing. If we knew the reaction force, if we knew it was 700 newtons at 32 degrees, then yeah, sure, we could pick the pivot here. But no, we couldn't because we couldn't solve for tension. You can only place the pivot where the beam is mounted. So you have to solve for tension first, and you can only find it summing our torques to 0. So, write it all down. Taking moment about P. So, I'll write it all out. R beam, weight beam, sine theta plus R weight sine theta equals R weight T sine phi. I'm just doing that because I want to color code just to make sure that students don't get caught out. All right. Now let's throw all the values in. 2 by 200 sine 40 plus 4 by 1000 sine 40 equals 4t sine 50. The total clockwise moment is 2,828, and that's going to equal 4t sine 50. Okay. And what do we get? 923 newtons to the left. Now, oh, by the way, perpendicular distance, this one's pretty easy. Our pivot point's down here. I would need to extend my force until I got a perpendicular distance. And again, same deal. If that's 4 and that's 40, then R perp is 4 sine 40. All right? So, I hope I've stressed to you enough. It is always going to be RF sine theta. Take the angle between the force and the line of action, and you will never get the answer wrong. Okay? Now, this question, as you see, it turns out it's a little bit easier than the previous example. Let's now solve it doesn't matter which way, you could do step 3 first if you want, but the way I teach it, let's go the verticals. Yo.
Is there any way the line of action could not act with the pivot?
No. If you take the pivot, then you draw a line to where the force is acting, and that's the line of action. Okay? So there's no component. Tension has no vertical component. So F, and that also equals 0. So that's negative 200, double negative, minus 1,000 equals plus 1,200 newtons. So hopefully that makes sense. If you've got a total downwards weight force of 1,200 newtons, then the reaction force has to cancel that out by having a vertical component of plus 1,200. Yeah, weight beam and weight. And then lastly, again, Fx is pretty easy, equals 0. It's Tx, well, it's just T really, we could just call it T, plus Frx. Let's make a convention that out of the wall's positive. So Frx equals negative, bracket negative 923 equals 2,923 newtons outwards. As we said, recombine. You don't need to draw a diagram if you don't want, but this is just because we're new to this. Okay. What you need to put down is the magnitude is 923 squared plus 1,200 squared is 1,500, 1.51 kilonewtons. Theta, arctan, opposite, over, adjacent, equals 52.4. So Kalis, it is just above the physical dimensions of the beam. Damn close. 1.51 times 10 to the 3 newtons. Right, 52.4 degrees above horizontal. Okay? Again, in fact, drawing in the vector diagram would actually be really simple. Why would it be simpler than the previous example? KK.
Field effect is either act down or that way.
Yep, so what shape are we drawing?
Right angle triangle.
Right angle triangle.
This.
Now, that is a simpler answer. Just draw a right angle triangle. It's Pythagorean. But remember, as I said, waist marking key needs you to show that you understand that it's in all three modes of equilibrium: rotational, vertical, and horizontal translational. Okay? So, guys, for you, I'll send out an email. The other class will have to watch that 12-minute video on this example. I want you to watch a 33-minute video to complete the next 2 pages. Then, when we get back on Monday, I'll show you some perpendicular distance questions where it is better treating the perpendicular distance. Yes, KK?
The question would be different if you're, for example, the ladder there. I know I copy the ladder, but if it's the ray is bent, it was like curved inwards.
Well,
it actually be perpendicular.
Well, okay, hang on. You've asked something very bizarre, but I've never heard it before. If the thing was curved,
Okay.
then we don't care about the shape. We just want where is its center of mass.
Right.
So if it was curved, then its center of mass would lie outside of the object. We don't care about. We would just simply draw a line to the center of mass.
So would there be different lines of action, sir?
No, you draw a line from pivot to that blue cross. That is your line of action.
But then if we had a tension acting at the top and the tension not acting with the line of action.
Yeah, the tension.
The tension is not the tension's acting from the pivot.
No, but
on the
if
top.
you attach like a cord at the top that's pulling the sausages and thing backwards, and then if the line of action's from
No, the other way.
Yeah. And
No.
then where any line of action, then the line of action is going through the center point.
The line of action is that.
But there's 2 lines of action.
No.
But then what about the center of
The
mass?
center point would lie on that line of action.
If the tension's acting there, I draw a straight dashed line from pivot to force,
Center of mass would be on that.
and I need to find what that is. No, the tension doesn't care where the center of mass is.
But then the center of mass is no longer acting with line of tension.
The tension isn't acting through the center of mass.
No, I mean the tension's
there
not
are
acting with
two
the
lines
line
of
of
action.
action. That's what I'm saying. So how would we solve that kind of
The
problem?
tension is not acting through the line of action. Well, I would identify here. That's where the tension's acting, right? That black dot, right? The pivot's still there, down there.
Yeah, so we draw the dotted line from pivot to center.
There, done. That's if
but
I now need to know. Okay, I would need to know how long is R, and I would need to know what is that angle.
But
You'd have to do some trick.
Is the center of mass is no longer in the line of action? So how do we solve it?
That's a different line of action. You've got a line of action to the weight,
Right.
and you've got a line of action to the tension.
Right.
Yeah. So so to answer, I now know what you're talking about. You can have different R values. All right. So it's just from pivot to force. Now, in all of these scenarios, they're all acting on a straight line object, in which case R is the same, and that one's down, and that one's up, and that one's down.
Yeah.
But absolutely, I could have an L-shaped ruler, and then you would have to you just draw from pivot to where the force is acting. You would then have to determine R and theta. Okay?
We wouldn't do anything weird with that.
I reckon on Monday, we're going to go through an example using perpendicular distance where the R values are different. They're not along the same common line. Hopefully it will make your question answered. Okay? So just chill till Monday. Guys, after you watch the YouTube lesson, you can now start hitting all of those questions, chapter questions, past test papers, all right? I realised this morning that you've got the weekend. I want you getting ready for the test, basically. So if I didn't teach you that lesson, then you're kind of just sitting there tapping your toes, waiting, and I don't want you to be rushing Tuesday night, Wednesday night. I want you to make a start now, okay? So thank you very much.